think we're going to get started this morning. Welcome everyone to Research Pays Off. We've missed a few months, but now we're back in production. And this morning we're going to hear a presentation about a couple of test cells that were constructed at MnROAD in 2017 related to reducing the cementitious material in our concrete mixtures. Really, we want to use as few resources as we can and also be more sustainable. Before we begin, I'm going to ask if Ben Worrell wants to chime in with any news on NRA.
Hi, this is Ben Worrell. Again, I don't have much of an update other than our call for innovation that was successfully in developing, I forget, it was 5 or 6 projects. Teams are working on those now. So again, that brings our projects that we have, over 20 projects that we're working on at this moment. And again, thank you for all the teams that are working on that. The executive committee did meet, and the notes are on the website if you want to look at those. Other than that, that's about all we have. We also are really working on our May meeting, and it might sound early to be working on the May workshop that we're going to have here in Minnesota for NRA. We want to have the agenda put together by TRB time so we can share that nationally and create interest that way. So that's all the update I had, Tom, so thank you.
All right, now we're going to begin a presentation with Dr. Hamad Sadati. He's an assistant scientist with the National Concrete Pavement Technology Center at Iowa State. So go ahead, Hamad, and take over, give us your presentation. You will have to unmute yourself. If that's possible. Ahmed?
Tom.
There we go.
So, great. Thanks for the introduction, Tom. And good morning, everybody. It's a pleasure for me to be here today and talk to you about the project and give you an update on the ongoing project, Reduce Cementitious Materials in Optimized Concrete Mixtures. First, I should say that the PI of the project, Dr. Peter Taylor, is traveling. Actually, he is on a plane right now. Unfortunately, he couldn't be here at this moment with us, so apologies for that. But I'm going to be presenting on behalf of Dr. Taylor, and hopefully I can do a good job on that. So today's presentation, I'm gonna go through the project just to refresh our minds. I'm gonna give you an overview on the project, what are the test cells and what are the pavement, design details, and we will have a review of the concrete material properties set on site and also in laboratory. And after that, we are gonna see a summary of the data gathered by the in-situ instrumentation placed in the 2 test cells, and we're also going
Ahmed, we lost your audio.
can you hear me now?
Yes, now we can hear you.
Perfect. So, as I was mentioning, I'm going to provide...
It sounds like someone else needs to mute their microphone. Thank you.
So, shall I continue?
Yes, I think you're good now.
Sure. So we are going to have an overview of the project, see the details of the pavement structure, and we are going to have an overview of the concrete material properties used for construction of the test cells for this project. And we are going to see some of the data gathered by the sensors and embedded in these concrete pavements. And we are also going to have a review of the pavement conditions as of mid-2019, the latest distress survey that we have had. So as Tom mentioned, in this project, we are trying to see the effect of reduced cementitious materials content in concrete mixtures. We are trying to see the potential effects on performance of concrete pavements constructed with such green mixtures. And of great interest for us is to see any potential issues that we may have with constructability of these pavements, and also the long-term durability and the longevity of these concrete mixtures and these pavements. So a few tasks are defined in this project to reach this goal. First, the research team started with a literature review, trying to see what are going to be the factors affecting the performance of a pavement with reduced binder materials, etc. And a report was submitted to the panel. And the pavement cells were constructed in mid-July 2017, and a lot of testing was done on both fresh and hardened concrete properties, and lots of sensors were embedded in these pavements, try to gather data over time and over the course of monitoring these pavements. And we have some sort of annual reports for these pavements, trying to gather all the observations during each year of monitoring to see if there is any considerable change in behavior of the pavements, or is there any specific behavior or observation that could be attributed to the reduced cementitious material content in these pavements. And as I mentioned earlier, there are going to be three main areas of interest in here. First is the analysis on early age properties and constructability of the pavements. Second, we are going to have the analysis on potential durability issues that can be correlated to the binder content in these mixtures and in these pavements, and also trying to project these observations, the laboratory data, the field observations, into long-term serviceability and economics of the pavement construction with reduced cementitious material contents. And hopefully the data we get through these project and through these years of monitoring these pavements are going to form the structure of a recommended specification for reduced cementitious material contents in concrete mixtures that are going to be used for rigid pavement construction. So an overview of the project location: we have two adjacent cells, number 138 and 238, as part of the low volume road of MnROAD research facility. In these two sections, for cell 138, we have a concrete mixture proportion with 500 pounds per cubic yard of cementitious material. We call it the section with low cementitious. And the second cell, cell 238, we have 470 pounds of cementitious material in concrete mixture. And we refer to this section as the section with lower cementitious material. So the pavement details of the pavement design and construction are identical for these two cells. We have 8 inches of concrete pavement cast over and a 5-inch thick base layer of class 5 aggregate. Panel dimensions are 12 by 15 feet socket joints in these two pavements, and we have 1.25 inch diameter dowel bars in transverse joints. And we are trying in this project to compare the performance and the data as much as we can with a reference cell, cell 524, cast with a concrete with 570 pounds of cementitious material. This section was also constructed in July 2017, and the main difference is that for this cell we have a pavement thickness of 6 inches and we are using 1-inch diameter dowel bars. So this section hopefully can serve as a reference for us to compare the performances, in-situ performance, and the material properties as much as we can. Here I have a summary of the mixture proportions. As you can see, section with low cementitious material, we have 500. With lower cementitious material, we are at 470 pounds per cubic yard of cementitious material. Both concrete mixtures are proportioned with a 0.42 water cementitious materials ratio. And in both of these mixtures, we have 25% replacement of class F fly ash. And here we can see this is the volume of paste to volume of void in aggregate, 146% and 137% for the low and lower cementitious mixtures respectively. So in July 2017, when the construction was ongoing, there was testing on job site done by both MnROAD staff, American Engineering Testing, and our colleagues at CP Tech Center, trying to address the fresh properties of concrete from different angles. First, we were interested in understanding the workability of these two mixtures. So we have two test methods which are part of the performance engineered concrete mixtures initiative as well. We use the Workability test and also the box test to see the workability of these mixtures and to see how these concrete mixtures are going to react to vibration. We also use the super air meter SAM test to see the quality of air void system in fresh state, also the air content, of course. And we determined the actual water cementitious materials ratio on site using the microwave test. Also did the semi-adiabatic calorimetry to monitor the heat of hydration of these concrete mixtures, and also used maturity sensors to have a good idea on strength development of these two concrete mixtures. And also the same day, samples were cast for testing these concrete mixtures for mechanical properties and durability and volumetric stability, as you can see listed in here. So going through the data, both mixtures had good air void system. The SAM number was less than 0.3 for both of the mixtures, 6.5% and 8.5% air in fresh state. But the actual water to cementitious material ratio in concrete made with 470 pounds, the lower cementitious mixture was a bit higher than the design value. The microwave test results are showing a 0.44 actual water cement ratio for this mixture, which we later on will see that's going to affect the drying shrinkage behavior of the concrete used in this cell. Regarding the workability, which we know is going to affect the constructability of the pavement in here, for the concrete with low cementitious material at 500 pounds per cubic yard, we had very good workability data. We had a box rating of 1, which corresponds to less than 10% voids on surface of the sample, as you can see on the left picture, and Kelly index of 0.88, which is well within the workability window recommended for workability test. But when testing this concrete with lower cementitious material, I mean 470 pounds of cementitious material, the box rating numbers increased a little. We had numbers of 2 or 3, which corresponds to like 30–40% of void on surface of the boxed sample, as we can see on the picture on the right side. And the Kelly index was 0.5, which is a bit less than what we like to see as a Kelly number for a good paving concrete. 2 samples were tested for calorimetry per mixture. No abnormalities were observed with the calorimetry data. A slightly higher heat of hydration with increased amount of cementitious material from 470 to 500, but totally same trends and no problems that could be attributed to the cementitious materials content. The same with the maturity data, exactly similar trends regardless of the binder content, same strength development behavior was expected for these two mixtures, which was also observed based on the mechanical property testing. The graph on top left side, I have the compressive strength development data, and the early age strength values we have in here are very similar for the two concrete mixtures, which are in good agreement with the maturity data we observed earlier. And the 28-day strength for both these mixtures was higher than 3,500 psi. And the 28-day modulus of rupture flexural strength data was higher than 600 psi for both of these concrete mixtures. A slightly higher modulus of elasticity with lower cementitious material, which can be because of higher amount of aggregate in that mixture, and a slightly higher shrinkage value at 56 days. Both numbers are low, but with reduced cementitious material, we would expect to have a lower shrinkage value, but because of that increase in water cementitious materials ratio, which was earlier shown in microwave test results, we had a slightly higher shrinkage value in here. But again, both of them are very low number, very good numbers. And comparable CTE data for both of the concrete mixtures, which could affect the deformations under temperature variations. A summary of the durability test data, we have the surface resistivity data, very comparable performance for both of the concrete mixtures with the numbers that could reach 25 kilo per centimeter at 90 days. Very good numbers we have in here for surface resistivity data, which could also be translated to formation factor and good index of transport properties of these two mixtures, which hopefully suggests a good durability in long term for these two mixtures. Also, the hardened properties of these mixtures were investigated in hardened. The air void system of the concrete mixtures were investigated in hardened state. We had very good spacing factor data, 0.002 inch for both of the mixtures, and over 5% air in hardened state for the two mixtures. Again, pointing to a good air void system and hopefully good frost durability in future. The only concern with durability data we had in here, I should say, was the numbers that we got for potential for oxychloride formation. We did the low temperature differential scanning calorimetry test in here, and the LTDSC test data we have are 0.186 and 0.205 for the potential oxychloride formation in these two mixtures. Typically, a number less than 0.15 correlates well with long-term durability against oxychloride formation, which can be manifested in terms of joint damage. But the thing is that the numbers we see in here, the oxychloride potential data we have in here, these are actually a factor of binder composition, the amount of fly ash we had in the mixture, not the total amount of binder in the concrete actually. So hopefully, potentially if we had more fly ash in these mixtures, we wouldn't see these two red numbers. But anyway, these two numbers do not have anything to do with the binder content actually. So no worries regarding the binder content in here. So, this was a summary of the fresh and hardened property data measured on these two specific concrete mixtures. But there has been a considerable effort going on in support provided by MnDOT and MnROAD research staff, doing a lot of in-situ measurements and gathering a lot of data from sensors. First thing, I'm going to go through the joint activation data obtained using the MnROAD system. So in September 2017, like a month and a half or 2 months after construction of the pavements, we went up there and used the MnROAD system, which is actually an ultrasonic shear wave tomography method, to see if the joints are activated in these two pavement cells. So each of the cells is like 260 feet long, and with 15-foot joint spacing, we had like 17, 18 joints in each of the cells. And all the joints were activated at that time. The MnROAD measurements showed that all the joints are fully cracked at the spots of measurements, and all the joints are activated at that time. So no abnormal behaviors and no problems in that regard. Continuing with in-situ measurements, falling weight deflectometer FWD testing is done on a regular basis by the research staff at MnROAD facility. So the test device, you can see a picture of it in here, and I have an example of the deflection basin data we have for one of the slabs in cell 138, and we have used these data to calculate the load transfer efficiency on these joints in these two test cells. So I have here a summary of the LTE data. For the experimental sections, cell 138 and cell 238, we have really comparable behavior in terms of LTE. The numbers are ranging between like 80-82% and reach as high as 97%, which are very good data and comparable data for the departure and approach slabs for both cells, for both inside and outside lanes. On the right side here, on the right graph here, I have the LTE data obtained for the reference cell, cell number 524. We can see a couple of measurements with LTE values lower than 80%, somewhere like 75 or 76%. But we should note that the reference cell we have in here had a thickness of only 6 inches compared to 8 inch for the experimental sections, so I would say good performance for this cell as well. And we also had a 1 inch diameter dowel in this cell. So overall, I should say we have had comparable data, comparable performance and acceptable performance in terms of LTE for both the experimental sections, regardless of the binder content, whether it's 470 or 500. The other test done by the research staff at MnROAD is the Ride Quality International Roughness Index. MnDOT's lightweight profiler is used for this purpose. Both the experimental sections and the reference cell were tested over time at different time intervals, both the inside and outside lanes, to see the variations in IRI values over time. Here I have the data for the reference cell with MRI values, mean roughness index values, which is the average of the left and right tire tracks here. And the numbers are ranging in a range of 100 plus minus like 10 inch per mile over time, not a considerable variation for the reference cell. And almost the same trend for the experimental sections. I should note that the inside lanes here shown with blue colored bars are the inside lanes where we had controlled traffic on low volume roads. So at different time intervals from late July 2017 up to early 2018, we have had IRI measurements. For the first 3 measurements, we have almost constant data in July, but after a couple months, starting with November data, we have a little bit of increase in IRI values, but almost constant observations afterwards, no significant change after that. And I would say, and as you can see from these 2 graphs, we had really comparable performance for both cells 138 and 238 for the first 2 years of monitoring. Strain gauges were also embedded in these concrete sections at different locations in corner and mid-edge at top and bottom of the pavement to monitor the response of pavement to dynamic loading. I should mention that the loading on these sections is done by the 5-axle 18-wheel truck with a weight of 80 kips. And these are the data, a sample of data I have for the dynamic load testing. Loading is done at two speed levels of 5 and 35 miles per hour, and data are gathered with a frequency of 1200 hertz. So here I have the one of the sensors reading at mid-edge bottom part of the pavement for cell 238, and I have readings for 5 miles per hour here. What I have done is that the blue lines that we have in here are the raw sensor readings, and I have taken the first 2 seconds data as the base of the measurements, and I have normalized the readings based on the first 2 second data. And here we can see exactly the, and we can trace the 5 axles of the truck in here. The average deformation values we have at 5 miles per hour for these 2 sections is less than like 10 or 15 microstrain in compression or tensile direction, for these 2 sections. And again, comparable behavior for the 2 test cells. We have comparable deformation magnitude, and in most places, deflection patterns as well, regardless of the mix type. And we have similar performance, similar data for the sensors located at similar spots in top corner or, for example, bottom corner, and so on. So again, both mixtures used in 138 and 238, they have the same properties, and the 2 pavements are exhibiting the same performance, same behavior, and same response to the dynamic load testing as well. Also important for the pavement, the environmental loading and deformations caused by environmental effects. In order to capture these deformations, vibrating wire strain gauges are used in pavements at 2 different depths, almost 1 inch and 7.5 inch from the top of the pavement. So we are covering the top and bottom surface of the pavement, and we have sensors in 2 locations again, at corner and at center of the slabs. So we have 4 sensors per concrete type per cell, and we are monitoring the variations in temperature in depths of the slab. And as you can see, we can have the thermal gradient determined for the slabs. Here, for example, I have the data for I think it's cell 238, where we can see a temperature gradient of up to 2 degrees centigrade, i.e. 3.6 degrees Fahrenheit per inch over the depths of the slab. And of course, such thermal gradients are going to cause deformations in terms of warping. So the vibrating wire gauges are also recording the in-situ strain caused by environmental effects. Here I have the data from cell 138. These are the isothermal measurements, so they only contain the deformations caused by shrinkage, warping, and curling. And we have seen that there is a kind of a tendency to change in strain magnitude and direction with seasonal variations in temperature, but overall we have deformations, strain values that can go as high as 300 microstrains, and the maximum numbers are observed at the surface of the pavement for the sensors located aligned parallel to the direction of the traffic. So the same type of data for cell 238. Unfortunately, it seems that we are losing one of the sensors in here the one at the top, we have a rapid increase in strain numbers, means that most probably we are losing that sensor. But overall, comparable performance and comparable magnitude of numbers for the two pavements. So again, no significant observation, no abnormalities observed in here that could be traced back into the binder content. So everything normal here. And of course, having a good understanding of fresh and hardened properties of the concrete mixtures, we can picture, the long-term performance of these mixtures. But in order to complete that picture, we are also constantly monitoring, of course, with help and support provided by the research staff at MnROAD. We are trying to monitor the performance of the mixture, the pavements, and we are considering distress surveys all the time. So the first crack that was observed in these two cells was in it was a transverse crack, kind of wide open, in cell 238 at the beginning of the concrete placement at 238, and it was first observed in February 2018. However, after a short while, we noticed that there are some increasing cracks. Here I have better picture. We have these kind of spider, like cracks forming adjacent to that wide open transverse crack. And the first time we noticed these cracks was July 2018, like 5 months after the initial crack was formed. So it was interesting for us to see the reason for this crack. So in collaboration with MnDOT, we went up there, and with their help, we had some cores taken from the distressed area, and also some cores from a good concrete section with no distress as a reference. So it was our plan to do petrographic analysis on the concrete to see if we can find anything specific or anything else of special interest. But it was interesting that the core that we extracted from the distressed area here, just adjacent to the cracks, when we pulled the core out, we saw that there is a considerable segregation in the concrete. The top part, the first 2-3 inches, was just pure mortar. And because we have this mortar at the surface and no coarse aggregates there to restrain the shrinkage and to provide steepness for the hardened concrete there, we had that cracking, which of course with the joint adjacent here and with the wide open crack, we could expect more penetration of water into the hardened concrete in here, and of course progressive cracking in future. And add to this matrix the load by the AT Gibbs truck. So the combination of these observations, I would say, were the reason for this type of crack in here. We still have the cores in lab, and we keep an eye on the crack propagation in this area. So we pulled 4 cores that day, 2 of them from the distress section and 2 of them from control section, 1 for inside lane and 1 for outside lane, exposed or not exposed to traffic loading. We took the cores back to the lab and cured them in water for a couple of weeks to make sure that they are going to be responsive to the resistivity measurements. We did the resistivity testing on these cores, comparable data somewhere between 80 to 90, 95 kilo ohm per second resistivity for the cores. And also at the day of coring, we kind of tried to see the permeability of the base layer. So we did the core hole permeability test at that day, and we kind of had a low permeability on at the base in the main crack location. And for one of the control locations, we couldn't do the test because we couldn't get stable readings. So these are the only cracks that we have seen so far in cell 238 with 470 pounds. And as I said earlier, we had some localized, variation in concrete quality, high concentration of mortar at surface in this area. That may have been the main reason for crack initiation and crack propagation in here, which I believe cannot be attributed to the and generalized to the rest of the pavement. So the properties we have seen in here cannot be really representative of the rest of the pavement. And of course, we have not seen any sort of that crack, any other place in cell 238. We also have one diagonal crack formed in cell 138. Seems maybe some problem with base and crack under load in here. I wouldn't consider this crack something really related to the concrete material properties. It would be some sort of a structural crack, but we can discuss it later. If you have any comments on that, I would be happy to hear the comments. And this is another view of that crack starting close to the intersection of the joints. We did like 30-35 degrees propagating in a diagonal direction through the slab. Here I have some pictures from the surface of the pavements to, refresh our minds on the pavement texture characteristics. These pictures are taken in May 2019. So the most updated pictures that I have. Here we have the cell 138, acceptable surface quality, no change in quality of the surface after 2 years of exposure to environmental condition in Minnesota. Here a close-up view of the transverse joint we have in here. Very good joint quality, very good surface quality, and another view of the surface texture for cell 138 with low cementitious. For cell 238 with lower cementitious material, 470 pounds of cementitious material, we have some, spots with, some voids on surface, not the very best finish that we could, expect for a rigid pavement, but these observations, these surface defects are kind of in line with the workability data that we got for the fresh concrete. So indicating that we can use the BKD test, to quantify the workability and to, response early in time, try to avoid these construction problems. Another view of the surface texture and good quality of the longitudinal joints in here, and very good performance so far. No strange behaviors, no other cracking after 2.5 years of exposure to controlled traffic loading and environmental conditions over there. So hopefully with the support provided by MnDOT and the research staff at MnROAD facility, we are gonna monitor these sections for at least 1 year more, try to see if we can observe any problems regarding the durability and in-situ performance of the mixtures that could be attributed to the reduced cementitious material contents. But based on the laboratory data and based on the sensor data and field test data and the distress survey and field observations, I would say that so far we have had acceptable performance for both test cells with 470 and 500 pounds per cubic yard of cementitious material. Some workability problems with lower cementitious that needs to be addressed for future projects, and because of that we had some problem with finishing, as we saw in the pictures. Other than that, we had no problems that could be really traced back to the cementitious materials content, no abnormalities in strength development, no problems with heat of hydration, and no problems with maturity of the concrete mixtures. Very good air void system, good durability indexes, and the only concern regarding durability was the potential for oxychloride formation, which again is because of the binder composition not the cementitious material content. And also the in-situ measurements, the FWD data, the IRI measurements all indicate comparable performance for these two mixtures and acceptable performance. No abnormal behavior so far, nothing that could be, you know, red flag or a warning that we cannot go with these binder contents, with these cementitious material contents for future construction projects. With that, I really need to acknowledge the financial and technical support provided by Minnesota Department on Transportation and the National Road Research Alliance. And I would also like to appreciate the technical support provided by MnROAD, especially Dr. Izebekai, Mr. Olsen, Mr. Van Dusen, and Mr. Varel, and Mr. Bernham. And also, I would like to appreciate the collaboration with American Engineering Testing, which did some of the lab works. With that, I should say this is all the slides and all the presentation materials I had for this morning, and I believe floor is going to be open for discussion and questions. Hopefully, we can discuss the findings here, and I can take the questions.
Okay, thank you, Hamad. Great presentation.
Thanks for the opportunity.
I will start questioning with, do you have concern that perhaps we will not see anything going on for 3 years? And maybe do you have a prediction of when we might see something, an effect of low cementitious content?
First, it's a promising sign that we do not see anything strange going on in 3 years, means that we have, acceptable performance so far. But yes, you are right. I think these sections are worth monitoring for longer periods of time, and we would definitely be happy to be part of this effort. And we would like to see the performances and monitor the performances after 3 years as well. Hopefully, if there is anything we can see at that time.
Okay, sounds good. Okay, so we have, please, audience members, please type in your questions and then I'll repeat them. We have a question that says, have we measured the coefficient of thermal expansion of different samples?
Yes, here I have the CTE values. Here is the CTE data, similar performance for the two concrete types.
Okay, great. Another question, is the segregation seen in the core due to overfinishing? Do you believe?
I am not really sure. I don't think it's because of the overfinishing, maybe just a hand placed section in that area, maybe. Unfortunately, I wasn't there at the paving day, and I couldn't find any thing that, in the pictures and videos we had from the paving day. We discussed the overfinishing as one of the options, but with this amount of cementitious material, 470 pounds, I don't think overfinishing is a main reason for this behavior. Most probably a hand placement, maybe.
Yeah, and I can chime in here and kind of say, just from experience of being around most of the sections that are built at MnROAD, that because of the small quantities, we often are short, even an eighth of a truckload. So what contractor will kind of pour as far as they can, and then they'll order just a very small truckload and they'll try to fill it in. So near the ends of the test cells, I think we encounter these problems quite often, again, because of the hand placement. So
yes, and the panels with these cracks were kind of at the end of the section.
Yes, so I think that's the case here. Is just
what you mentioned here.
Yeah, when we look at the performance of these sections, we need to look kind of in the middle when the slip-form paver was going through, and kind of stay away from the ends, because it's very hard, it seems, to predict exactly how much you need to fill up a test cell.
Exactly.
Okay, another question. It says, what other test sections around the country have cement content as low as what was done at MnROAD? And if so, was the performance tracked?
I am not really aware of any other test sections with these amount of cementitious materials, but it's a good question to search for such sections and see if we can compare the behavior. Very good question. But unfortunately, I'm not aware of any other sections. If any other researchers online in here can help us with this question.
Yeah, I understand there's certainly specifications out there that go as low as 500, but the contractors have been very nervous to actually pave that low. So
yes.
Okay. Second part of the question was the cracking due to the sensor in the area? It says look at slide 28 or so.
Let me go to slide 28. No, it was not because of the sensors. Something I have forgotten to say, that the first wide open crack in cell 238 we saw is most probably because of a utility pipeline going, crossing the pavement in here. Here we see this utility box on side of the pavement, and there is a line passing underneath the pavement in here. Most probably something to do with that, but we did not have sensors in here, so not because of the sensors themselves.
Yeah, and I would agree that actually the first test section we had back in 1993 actually developed a crack very similar in that area. So there's obviously a trench or something in there that keeps heaving up and down.
Yeah, most probably, yes.
Yeah, so that's not surprising. Any further questions from the audience? Feel free to unmute yourself and chime in, or again, type your question into the comment box. Hearing nothing, I don't know, Ben, do you have anything to say about next month's Research Pays Off webinar?
This is Ben Worrell. I do not. I guess we are looking for topics. We're wanting to focus on projects like this one, where it's an NROAD effort, and to allow many teams to kind of sneak a peek at what's going on in that research area. So we'll be coming up with a topic area. If anyone's out there that's working on an NROAD project and is ready to present, let us know. Otherwise, we'll be picking one or two and going with that.
If there are no other questions, I thank the presenter and the audience members, and we look forward to seeing you next time.
Great. Thank you for the opportunity.
Thank you.
Nice job, Tom. Ahmed.
Thank you, sir.